In this video, we'll attempt to evaluate the improper integral of log of x over x. We'll look at it on the interval from 1 to infinity. Before thinking about the improper integral, let's just think about whether or not we'll be able to find an antiderivative for this expression. To give an indication of how we might do this, I'm going to factor the expression as log of x times 1 over x. And I do that because right here we're seeing the derivative of log of x as a factor of the integral. That suggests that I try taking u to be ln of x as a substitution. Its derivative will be 1 over x dx. So its differential rather will be 1 over x dx, and that will substitute out this part of the integral. And so we'll see a new integral of the form u du. Now this is an improper integral and it has limits of integration, so we should change those and replace them with the corresponding values for u. When x is equal to 1, I need to find the value of u, and u is defined to be the log of x, so we're asking for the log of 1, and the log of 1 is 0. Similarly, I need to look at what happens as x goes to infinity. I need to look at the limit as x goes to infinity of u. That means to take the limit of the log of x, and as x becomes large, the logarithm grows slowly but does go to infinity as well. So my new limits of integration will be 0 to infinity for the improper integral. As an improper integral, it is a limit. I'm going to let b be a placeholder, and we're going to take the integral from 0 now to b, and we'll let that upper limit of integration b go to infinity. We're integrating the function u du. The antiderivative is very straightforward here. I'm going to find the antiderivative of u, that's u squared over 2, and I evaluate that from 0 to b, and then I need to take the limit as b goes to infinity. And you can start to anticipate what the issue might be here. As I evaluate this at the two numbers, I'm going to have to evaluate it at u equal to b, and when I do that I get b squared over 2. And I evaluate at 0, that gives me 0 squared over 2, which of course will be 0. And as b becomes large, this term here will go to infinity, giving me infinity as the answer for the limit. And therefore, this improper integral diverges. It is not a finite amount of area under this curve. Let's draw a picture of this curve. There it is. As x approaches 0, you're going to see this logarithm drive the function down towards negative infinity. When x is equal to 1, the log is 0, so we're seeing this x-intercept here right at 1, and that's where we're starting out integration. If I was to integrate a finite amount of area from 1 to b, I would be integrating the portion of the expression above before we took the limit. That's the integral from 1 to b of my function. We found a formula for that right here. It's actually this b squared over 2. This shaded area is growing quadratically as I move b to the right. What's happening here is that this integral is diverging because what's left to come here under the curve, this portion of the area to the right of where I'm ending my integration, is in fact arbitrarily large. If I increase b, I can accumulate as much area as I want, and it will do so quadratically according to b squared here. So there's still an arbitrarily large amount of area to come in this red portion under the curve, and so there is not a finite amount of area from 1 to infinity, and this integral diverges.